Before modern computers were invented, mathematicians asked a very simple question. Can every mathematical problem be solved by following set of steps or rules? To answer this, in 1936, a British mathematician, Alan Turing, proposed a simple yet powerful idea. Today, we are going to deep dive into one of the most foundational concepts in computer sciences, the Turing machine. So the question is, what is Turing machine? A Turing machine is a mathematical model of computation that describes an abstract machine capable of manipulating any task by following a specific step of rules. Whoa. In simple words, you can imagine it is a machine capable of reading and writing symbols on an infinite tape, and surprisingly, that's all what you need to perform any modern computation, what a modern computer can do.
So, how actually a Turing machine works? It has four main components: an infinite tape divided into cells that stores the symbols, a read-write head that scans one cell at a time and can move left or right, a finite set of states, which is also known as the sets of instructions, which keep the track of the current conditions or the state of the machine. So, let's consider all women a computer. This woman a computer. First, she is given a set of instructions. Second, she is given a paper on which she can write symbols or alphabets following the sets of instructions. Third, eventually she can erase or rewrite the symbols following the sets of instructions. And fourth, when she is finished with her computations, she will stop. Now replace this women with a scanning head. This scanning head can read a symbol at a time, and at the same time it can erase it and rewrite it. Now this piece of paper can be replaced by an infinitely long tape. But how does this Turing machine knows what to do? You see, when this woman is reading or writing the data, something is going in her mind. This is what Alan Turing named a finite set of states or a finite sets of instructions. These states tells the machine what to do, and this can be only explained perfectly by diagrams and visuals. We'll create a state table, or we'll give this machine a task to recognize whether there are even or odd number of ones and zeros. Now, each cycle of this state table has to pair with 1 zeros and 1 ones. It looks a bit complicated, but it isn't it that much. Machine starts in the start state. If the machine finds 0, it replaces the 0 with the x and moves to the state B. If it finds 1, it replaces it with x and moves to the state C. If it finds x, it leaves it alone. If it finds blank spaces, it means the pairing has been done. After reading 0 and replacing it with x, now the machine needs 1 to pair with. So it will move to the state B, which will tell the machine that if it finds 0 or x, it will skip them and move next to find 1. When the machine finds 1, it replaces it with x and move left to enter the state D. The state D tells the machines to start the whole process from beginning. Now the machine repeats the whole process, and after one round, the machine only encounters x's. After encountering all x, machine encounters blank spaces, which means all ones and zeros are paired up. So, it means that the state table can be replaced with the different instructions to calculate square root, multiplication and addition.
Turing machine is considered as one of the most important concepts of theoretical computer sciences because it tells us about the limit of computation, and it also tells us about what can and what cannot be done by the computer. Before Turing machine, there was no clear understanding of what computation actually meant, but his model gave us a precise mathematical way to describe algorithms and problem solving. It became the foundation of the computability theory, which studies how effectively a problem can be solved, and it also tells us about how hard or easy the problem is based on the available resources such as time and memory. In short, the Turing machine provides us a universal standard for understanding all the kind of computation, the same standard that every programming language and algorithm is built upon today. Even though the Turing machine was a theoretical concept, its principles still live inside every modern computer that we use today. When a computer runs a program, it analyzes data, performs calculations, and stores the result just like a Turing machine's head moving across its tape. The concept of a universal Turing machine, which can directly read description of other machines, has directly inspired the today's design of computers, which can be collectively known as the von Neumann architecture. So whether it's your laptop, smartphone, or even a supercomputer at NASA, always remember that these are just practical versions of Turing's original model, which was built from scratch with a faster software and a complex hardware.
Our Turing machine works by reading an input, performing an operation, writing the result, and then moving to the next step. Surprisingly, a CPU does something very similar. It follows a repetitive cycle known as fetch, decode, and execute. First, it fetches an instruction from the memory. Then it decodes what that instruction means. Then it executes that instruction and stores the result before moving to the next step. So, even though today's computers are extremely powerful, but the core idea behind their functioning is the same step by step logic introduced by Alan Turing almost a century ago. Another example is artificial intelligence. Whether it is a simple calculator or complex AI model, every system runs through algorithm, a set of instructions, which was also introduced by Alan Turing. This means that modern computing, from basic machines to advanced technologies, is still built on Turing's original theory of computation.
Now for our video format, we use the MP4 format because it provides the excellent quality with the small file size, making it ideal for uploading and sharing online. We also explored other formats like AVI. It offers high quality but results in large file sizes, making it less efficient for the online submissions. MOV. It's great for Apple devices and professional editing, but it's not as universally compatible as MP4. That's why we chose MP4. It's lightweight, widely supported, and delivers the great quality of the video.